Hi everyone, welcome to your next class of Gen Chem 1 with me. This is a little unusual, I know, but as I announced earlier this week, I'm out of town on Friday right before our fall break and didn't want us to miss any class time. So I'm recording myself delivering what I plan to be Friday's lecture using a neat technology called Swivel. Just so you get used to it a little bit, I'm wearing a little tag right now, and it allows the camera to pan and follow me around. So you'll see me move back and forth in front of the boards, and hopefully I'll write large enough on the board that you'll be able to write and follow along and take notes just as if we were in a regular class session. I'll try to keep the class a little briefer than usual, hopefully, in the interest of your time and keeping you interested while you watch. So let's dig right into the new material from Chapter 5. Chapter 5, we're moving forward in our online text, talks about thermochemistry. Thermochemistry is the word that we use to describe the study of energy in chemical systems and chemical reactions. There's a lot of energy to be had, released, in other words, in a lot of chemical processes, as well as a lot of processes that absorb a tremendous amount of energy in order for them to happen. So some of the big picture questions that we'll look at in this first session are, what is energy and how do we quantify it? How do we go about, what are the units of energy? Okay, what are some of the different terminology that you maybe have heard of with energy? And then perhaps more importantly, in terms of the skills that we'll gain today, how is energy measured in chemical reactions and chemical changes? So those will be the two big picture issues that we take up today. So as far as, what is energy, we define energy as the ability to do work. This is a very physics definition to us, but it's true. This is what energy is. It's the ability to do work. Now, work is done when a force is applied to move an object some distance. This doesn't happen a whole lot in chemistry, to be honest. We think about some of the chemical changes that you've witnessed in lab. You're not seeing forces moving objects, tremendous distances, like lifting a pen. That's work that I just did right there. Okay. So we'll have to look a little more creatively for where the work might be done in chemical systems. And then we'll actually see that that work isn't the only way that energy is involved in chemical systems, as it turns out. Okay. You may have heard of the terms kinetic energy and potential energy. Not that we're going to distinguish too much or use either of these very much, but kinetic energy is energy associated with motion. Anything moving has kinetic energy. Now, that's important because in chemistry, molecules are always moving. So, all chemical systems have some amount of kinetic energy present in them. Even the molecules of a solid or the atoms of a solid are vibrating back and forth. And so there's some degree of kinetic energy there. Potential energy is energy that is stored energy, like energy that could be used later on, sort of like a bank account of energy that you could withdraw from or add to. Okay? In chemistry, this is present in our chemical bonds. Chemical bonding is a topic that we'll take up in a couple of chapters of time from now, but it's very important. And one of the main things that we're interested in chemical reactions is how the bonds change. So that's where our potential energy comes from in chemical systems. The primary units that we use for measuring energy are the calorie and the joule. The calorie is the original one. And when I say original, it was the first unit defined for energy. The joule is now the SI one. So this is the unit that we should be using more often than not. Okay. The relationship between these two is that 1 calorie is equal to 4.184 joules. That 4.184 we'll see is a sort of a special number. It comes back into play a little bit later on in today's lesson as well. Now, if you're wondering, this calorie with its lowercase c is related to, but slightly different from, the calories that we're used to hearing about on our food, right? If you look at any food product that has a label on it that tells you about the nutrition, the calorie listed on that will have a capital C. And they're not just being formal when they do that. It's actually a different unit. That capital C calorie, or what we call the dietary calorie, okay, because it's part of the food in our diet, is equal to 1,000 of the real lowercase calories. All right? So when you see a snack, for example, that might advertise itself as 250 calories, it's actually, 250,000 real calories. If you multiply that by about 4, you're pushing 1,000,000 joules, as it turns out, or a megajoule. So food contains a lot of energy. This is a takeaway message from that little example right there. Okay? So we can use this relationship just like a foot equals 12 inches or a meter equals 100 centimeters. This is how we would convert back and forth between our different units of energy, the calorie and the joule. Okay? Now, what we're also often seeing in chemical systems is thermal energy. And this is a form of kinetic energy. So let's talk a little bit about thermal energy. Okay? As molecules or atoms, okay, gain energy, they move faster. Okay? Or we could say they move more. They could move farther, depending on if they're a gas. Okay? And the temperature of an object is a measure of this motion. Okay. So I'm going to get into a couple of different terms that sometimes get mixed up and interchanged, and we want to make sure that we're using them correctly so that we're all on the same page. When I say there's a certain amount of heat, or when I talk about the temperature. So let's define a couple of these terms just to make sure we're all working together and using them the same way. Temperature is a measure of a system's ability to transfer energy in the form of what we call heat. All right. So there's another term that we're going to have to define. All right. Heat's a tricky word. We think about heat when we talk about heating our homes. We think of something as being hot. That's where this gets associated with the word temperature, right? It might get a little bit confusing. When we use the term heat in a chemistry context, we're referring to a quantity of energy, okay, that is transferred between two systems. Okay? So, to give you an analogy that maybe will resonate with you, let's talk about money for a second. Temperature might be sort of like saying how much money is in your bank account, right? That's a measure of your ability to maybe transfer money, to give money to other people. Heat would actually be money that you are then giving to people or receiving, like your paycheck coming in, right? Or you writing a check, giving money to somebody else, right? The little transfers that you make in and out of your account, that is heat, all right? Temperature is just the balance, the total amount of money in your account. It doesn't all have to come out as heat, right? I like to keep a minimum amount in my bank account, and therefore only what's in excess of that minimum amount is what would be the heat associated with my bank account, right? Because that's how much I could transfer in and out, keeping in mind that I want to keep that sort of that safety net of a balance in there, okay? It's these heat quantities, these amounts of energy that move in and out of systems that we measure in chemistry frequently. And we measure these for many chemical reactions and changes. And here's one of the reasons why. Well, let's go back to the money analogy. If I, give you money, 2 bank account balances have now changed. My bank account has gone down, and your balance has gone up as a result as well, right? And so we can track the total amount of energy, right? The total bank account balances, and we can understand what's happening in the entire universe of banking by keeping track of all the little transactions that we have, right? It's very difficult to know the total amount of energy in many chemical systems, as it turns out, right? It's a private question for you to ask me, what's the total amount of money that I have in my bank account? And it's really complicated as well because I have my savings account, my checking account, I have some retirement accounts, maybe I have a college savings account set aside for my children. And so there's a variety of different places where my total amount of money is stored. Just as in a chemical system, there's a variety of different, very small accounts in which the energy is placed or stored. And so getting all of that would be very difficult. Knowing all that would be challenging. But we can figure out how it's changing just by looking at the energy transactions, the transfers of energy between chemical systems, which occur through this thing called heat. So it's really important that we be able to track heat. Okay? So there are 2 ways that heat can be transferred. Okay? 2 scenarios, let's call them, involving heat transfers. The first one's the more common sense one. A temperature change occurs in a system. All right, this one makes a lot of sense with the banking analogy, right? If I write a check for $100 to someone, then my balance goes down $100. Like my temperature decreases by $100, and that other person's balance goes up by $100. So that's where it's really easy to understand that there's been a transfer of energy when the temperature changes for a system. Okay? In these situations, the heat is calculated, and the symbol of heat is Q, by the way. Okay? The heat is calculated depending on 3 variables of the system. The mass of the system, a constant associated with the system, for now I'll label it CSP, times the change in temperature of the system. Okay, again, M is equal to the mass of the system. CSP is what we call the specific heat capacity. Of your system or of your object, okay? And then delta T, change in temperature. When we calculate a delta, this is the Greek letter delta, if you haven't seen that before, it means the change. It always means the change in a mathematical or chemistry context. So we always calculate deltas by taking the final value of that variable minus the initial value of that variable, all right? And depending on what those 2 are, that could lead to it being a positive or a negative value, which is fine for us. In fact, that's very important for us as we'll talk about the sign associated with heat changes. Okay? So these are the 3 variables that we need for calculating the heat flow when there's a temperature change in a system. The other possible scenario is that there is no temperature change, but there is still energy being given off due to a chemical rearrangement. Okay? This would be a chemical reaction, in other words, i.e., a reaction. Okay? In that case, the heat is found very differently. It's equal to N times delta H of the reaction. N is going to be moles, and delta H is something that we'll define a little bit later on, so I'm not real worried about it right now. It's called the enthalpy of the reaction. Okay. So what's important in this scenario number 2 and in the formula Q equals N delta H is that you see there is no temperature change. There's no delta T occurring there, all right? And that's the clear difference as to how we'll know which formula to use at any given time, whether to use the Q equals MC delta T or the Q equals N delta H. All right, for today's work, we'll be focusing more on the temperature change associated with heat flow. So let's look at a couple of examples and do some calculations with that formula. All right. Now, just like money and how you can spend money or you can earn money or be given money, right? Heat can enter or leave a system, and it's going to have a different sign, okay, positive or negative sign, depending on the direction in which the heat flows relative to the system. So I think we'll see that in these two different examples that I have for us here. Okay. So first, let's calculate the heat gained. Calculate the heat gained when 360 grams of water are warmed from 20.7 to 46.9 degrees Celsius. Okay, calculate the heat gained when 360 grams of water are warmed from 20.7 to 46.9 degrees Celsius. Right away, I want to note that we see a temperature change. We see two different temperatures, which implies we're going to be using the Q equals M CSP delta T. So the three values or variables that we need are the mass of the system, which is given, the heat capacity. So we would have to look this up. The heat capacity for water as a liquid, right? Any material that exists in its different phases has a different heat capacity in those three different phases. So when you look up the heat capacity of water, you have to carefully make sure you're finding the liquid phase. So for water, it is that number we saw earlier, 4.184 joules per gram degree Celsius. All right. What this means, if you want to interpret what this means, is that 1 gram of water to be raised by 1 degree Celsius on a thermometer, right, requires 4.184 joules of energy. Now, 1 gram of water is only a milliliter, right? So maybe now we start to come back to that dietary calorie that I was mentioning a little while ago, and why our food has so many units of energy in it. Because a gram of water, or 1 milliliter, to change its temperature by just 1 degree Celsius doesn't require much energy. Right? Now you think about your human being system is 100, 150, 200 pounds, and a lot of that's water, right? And to continue to regulate your system on a daily basis requires lots and lots of energy. There's lots of stuff going on inside us. Okay. Anyway, this is a constant. If I change this from water to a different liquid like ethanol, or pick mercury, all right, or for a solid, no matter what that is, we'd be able to look up and find its heat capacity. A large number of these values are listed in Chapter 5 in our textbook, by the way. Okay, so you can scroll through and find any constants that you might need. And in ALEX, it would give you, it would be one of the tables of information that you can access in any given problem if they're not provided. All right. So let's come back to calculating our Q now then. We just plug everything in, 360 grams, 4.184 joules per gram degrees Celsius. And then the delta T, again, is T final minus T initial. So our final temperature is 46.9 minus our initial temperature, 20.7. All right. If we carry this through, you'd, of course, want to do this first. So you'd come up with about 26.2, and then multiply by 4 and by 360. You get a rather large number, 39,500. Your units are just joules because you get grams over grams canceling out and degrees Celsius over degrees Celsius, which cancel out. When the values are this large, we tend to convert them to the kilojoule scale. So this would be 39.5 kilojoules. All right. Notice that this has a positive sign. Q is positive when heat is gained or absorbed, added, a bunch of different words, okay, by the system. If we turn around and let this water, this exact same 360 grams of water, cool back down from 46.9 to 20.7, all right, we would see the release then of energy, and it would be the exact same amount of energy. The problem would be solved exactly the same way, just these two numbers would switch places, which would make that a negative 26.2 degrees Celsius, and then make this a negative 39.5 kilojoules. Right? That idea that it's the exact same amount of energy gained and lost is the first law of thermodynamics. We've heard of the law of conservation of energy back when we were starting to look at chemical reactions. We have the law of conservation of energy. Sorry, I said law of conservation of mass is what I meant a second ago when we were looking at chemical reactions. But we have the law of conservation of energy as well, which tells us that there's going to be no net change in the energy of the universe for any reaction process that occurs. So when this water gains energy, something else loses energy. If this water loses energy, something else gains energy. And so we can apply that. We will apply that shortly, actually. Okay. So for now, though, the big thing is the sign of this. Q is positive when heat is gained. Q is negative when heat is lost, or another word that's often used is released by the system. So those are your two signs for Q, positive and negative. Let's put that negative sign to use, and let's twist this example around a little bit, or this formula around a little bit, and do another one. So we're not always going to solve for heat, actually. That formula, Q equals mc times delta T, has four connected variables in it, Q, M, CSP, and delta T. So we can solve realistically for any one of them. All right? Here's a little bit more advanced version of a problem, and it's likely you'll encounter something like this in ALEX. A 1.1 kilogram copper pot initially at 100 degrees Celsius loses 32.7 kilojoules of energy as heat. Loses 32.7 kilojoules of energy as heat. Okay. What is the final temperature of the pot? So in this problem, we are now going to be looking for not the Q. We're given the Q. We're going to be looking for one of the other variables. And it's actually not the delta T. I'll break this out a little bit further. We're actually going to break out delta T into T final minus T initial. And the thing that we're looking for is this final temperature. So this is really just an algebraic enhancement of the previous problem that we had. So we're given the mass of our pot, right? We're given the initial temperature. We need to look up the specific heat capacity of copper. The heat capacity of copper, again as a solid, is 0.385 joules per gram degree Celsius. Okay? With that, we can start to plug in some values here. Now, notice I'm going to take my lead from the heat capacity. Its units given to me involve the joule and the gram and degrees Celsius. My heat was given to me as 32.7 kilojoules, so I'm going to convert that to 32,700 joules so that it matches the joules in the heat capacity. The other important thing here is that this is negative because this was lost, right? The key word, this copper pot loses energy. Its energy is decreasing, and so according to the signs that we just defined over here, a negative sign is associated with Q when heat is lost or released by the system. Okay? We won't get the right answer if we don't put this in here. Right? We can think about what the answer needs to be, right? If our pot is losing energy, it starts at 100, the final answer should be something less than 100. If you didn't put this negative sign here, you'd predict a final temperature higher than 100. All right? And so you should catch that mistake if you were to make it. Right? It makes no sense that the pot would lose energy and get hotter. Okay. All right. Our mass of our pot is 1,100 grams. Again, I'm matching what is in my heat capacity. So I took the 1.1 kilograms, multiplied it by 1,000. It's 1,100. Okay. 0.385 joules per gram degree Celsius. And then T final minus, I can plug in the initial 100 degrees Celsius. Okay. So I have a little algebra problem here, a little distributing to do here. This looks like I could, what I'm going to do here is multiply these two right here. It's going to give me about 400 or so, okay? And then I've divided it over here. So after I divide it, I've got negative 77.2 on the left side. And on the right side, I have T final minus my 100 degrees Celsius. Okay? So again, the two steps that I did there was I did this multiplication, and then I divided that term to the left side to free up the variable. So now all I have to do is add 100. So my T final is 22.8 degrees Celsius. Okay? That answer now makes sense, right? We said just a second ago that as the copper loses energy, it's going to cool, all right? And that would decrease its temperature. Okay. So paying attention to the sign is very, very important. Okay. Now, a minute or two ago, I referenced something called the First Law of Thermodynamics, the first law of energy, essentially, the law of conservation of energy. And that law gives us some very important practical techniques that we make use of in the chemistry lab. So this first law of thermodynamics says that in symbolic terms, the change in energy of the universe is equal to 0. Okay? Again, this is really a sentence. The change in energy of the universe is equal to 0. And we could add to that, during any chemical reaction, during any chemical or physical change, all right, at any time, the net amount of energy in the universe is constant. Right? So we just looked at 2 previous problems, though, where some water warmed up or where a copper pot cools down. And clearly we're seeing a change in energy of the copper in this previous example or of the water in the one before that. So why isn't the energy changing there? Well, the trick is perspective. Here we're looking at just one tiny piece of the universe, the copper pot. We failed to consider the rest of the universe. If we think about the entirety of the rest of the universe, we could divide our universe into 2 parts. The change in energy of the system that we're interested in, plus the change in energy of the rest of the universe, which we'll often call the surroundings. So the sum of these 2 would equal 0. So if one goes up, the other goes down, as it turns out. Okay. Now, in most chemical reactions, here's where we start to make some interesting assumptions here, but in almost all chemical processes, heat is the only way the energy changes. Okay? So this equation right here is acknowledging the total change in energy. Heat is one way. We'll talk briefly in probably our next class about work being the other way to change the energy of a system. But we don't have much work in chemical processes. So heat is really the main way that this happens. So that means that a quick estimate of the change in energy of our system is the heat flow into or out of that system. Thus, the other quick estimate of what's happening in the surroundings would be the heat change of the surroundings. This allows us to observe one or the other and to know what happens to its partner. The heat change of a system is equal to, but opposite in sign, the heat change of the surroundings. And measuring one lets us infer what happened to the other. So when our copper pot loses all this energy, the rest of the universe is gaining it. Okay? Or when our water is warmed up, the rest of the universe is providing that energy to allow that to happen. All right? The experimental process of following these transfers of energy or these relationships is known as calorimetry. So calorimetry is the experimental process of following heat flow between a system and its surroundings. All right. We have a variety of different tools to do this that we call calorimeters. Look at the notes that I've posted in Moodle. Skim through your textbook, and you're going to see a lot of pictures of these calorimeters. You'll use one in lab after the break, once we restart lab a week or so after the fall break. All right, so you'll be very familiar with this material by the time you use it. But we have a bunch of different styles of calorimeter, depending on the kind of system that we're interested in looking at. We'll use a fairly simple one that's very good at letting us study liquids. Okay? The basic idea of a calorimeter, though, is that you have a layer of insulation, some kind of insulation. What you're doing by creating this insulation is that you have inside the insulated area then a mini universe. all to itself. And that's important because the change in energy of that mini universe is equal to 0 if this is a well-insulated material. I got my coffee cup with me as usual, right? It's a pretty good coffee cup. My coffee stays hot in this for hours because the cool air, literally all around it here, is not able to absorb the energy. The energy does not come out from my coffee into the air surrounding it. All right. If I put a cold drink in here, nor would the hot, warm air, if I took my cup outside today, get into my cold drink. It would stay cold on the inside. So if you can create that small, mini version of a universe, you've got the first law of thermodynamics that's applying there. Then inside your universe, you can put two different things. Maybe a liquid and a solid. If you treat the solid as your system, the Q of the solid would be equal to, but opposite in sign, the Q of the liquid. That's your first law, right? You've broken your universe into two parts, the solid and the liquid. The total change in energy of both has to equal 0. And now you've set the stage for a calorimetry experiment, all right, where you can figure out what happens to one piece by observing the other. What do I mean by that? So what if we want to know about how this solid's temperature is changing? It's hard to stick a thermometer right into a solid, right? I mean, if my hand represented a rock or something, I can't stick a thermometer into it to measure its temperature change. But I can measure the liquid. And so if I stick a thermometer in the liquid and then put the rock into it, I can measure how the liquid's temperature is changing. And the first law is telling us that the liquid's behavior is related to the solid's behavior. So we can infer from the liquid what might have happened to the solid. And this is the classic scenario for calorimetry experiments, just like you'll do in lab in short time. Okay? So what we would do in a problem like this is measure, for example, the temperature change of the liquid. So we'd have an M of the liquid times CSP of the liquid times delta T of the liquid. So if we used water in our calorimeter, we could weigh how much water we added to it. We know its heat capacity, and the thermometer would give us the change in temperature of it. And then that would equal what's happening for the solid, the mass of the solid times the heat capacity of the solid times the change in temperature of the solid. If we knew what the solid was, we'd have its specific heat capacity. We'd have weighed it, so we'd have its mass. Thus, we'd be able to find its change in temperature. A clever twist on an experiment like this, if we did not know what the solid's identity was, we could weigh it, and then if we could get its starting and final temperatures, all right, which is possible, even though we can't directly stick a thermometer into it. Okay, there are other ways to do that. We could infer or calculate what the heat capacity of the solid was, which would be a way to identify it, just like having its density would be another useful tool for doing that. Okay? So I'll give you an example of how we do this when we come back together live for class after the break. But I think that's a pretty good stopping point for today. So just to review real quickly and have you up and running with me when I see you on Wednesday after the fall break. We've introduced energy today, the ability to do work. But more importantly, all chemical changes, all chemical processes involve a transfer of energy between the system and its surroundings. We measure that with the joule or calories, all right? And the technique that we'll use to measure it is known as calorimetry. Okay? There's two different ways to quantify or measure heat flow between systems. When a temperature change occurs, we use our MCSP delta T formula. When no temperature change occurs, which is involved in a chemical reaction that's occurring at constant temperature, we'll use a different formula, which I'll certainly be showing you how to use in the near future. Okay? Thanks for watching with me today. I hope you've had a good break and that you've watched this before the very, very tail end of break. And I'll see you in class on Wednesday after break. Have a good one.